Right, hi everyone. Now we're trying to cover midterm 2017, and yeah, we may go quickly through some of the questions that are similar to past midterms from 2019 and 18. Now we're starting with question 1. Now we're saying in order to jump off the floor must exert a force on you. Now, the correct answer highlighted is C. It's opposite to and greater than your weight, okay? Now, imagine you're standing here on this schematic, so let's represent this. So here you are, or maybe let's draw it just next to it. So you are here, okay? Now, here you are under the effect of gravity, of course, so mg. And then there's the normal. Okay. Now, for you to jump upward, of course, you need to accelerate upward. So, according to Newton's second law, if we're taking the positive y direction, we're pointing up. So, the net force along y will be equal to mass times acceleration. Now, what are the forces acting? We have normal, positive, minus mg. Okay, so mg is pointing down, so that's minus, equal to mass times acceleration, which means normal equals to mg plus ma. So that means the normal will be greater, okay, greater than the weight. So that's why we're having here opposite to, okay, so the normal is opposite to and greater in magnitude to the weight, okay, and greater than the weight. Right, so that's question number 1. Question number 2, we have a student in an elevator is checking Newton's law using a scale. Now the scale is showing a reading that is lower than student's actual weight. Which statement explains this phenomenon? Now we're talking about the apparent weight. We had similar questions in the other midterms. Now we're talking about, again, a student here standing on an elevator. We've seen this question countless times now. And you remember this formula for the apparent weight, so given by the normal. Now, if acceleration is positive, you remember the normal will give you an apparent weight that is greater than mg. If acceleration is negative, okay, so the apparent weight will give you a value that is less than mg, okay? Now, because we're reading, the scale is showing a reading lower than student's actual weight. Now, if it's lower than student's actual weight, that means what? The elevator is moving with a negative acceleration, okay? So the elevator is moving with a negative acceleration. Now, what is this? So this is the elevator. If we take the positive y direction pointing up, so positive acceleration will be pointing up, negative acceleration will be pointing down. Okay. Now, in this case, the correct option is option C, and it's telling me the elevator moves downward with increasing speed. So that means acceleration is indeed pointing downward. Okay, so it's a negative acceleration. It's, yes, speeding up, but moving downward. Okay, that's still a negative acceleration according to the positive direction we're having here. Okay. Right, so this is question number 2. Now moving on to question number 3. Now we have the following. So a truck is initially at rest on a level road with the engine on and has a crate in its cargo bed. Now the truck is suddenly moved forward and the crate slips backward against the cargo bed. Which of the following statements is true regarding the motion of the crate? Now, of course, we had this actually today, okay, from midterm 2018. And remember, we had this drawing. 1 second. Let's use the pen. So this is, let's say, this is the truck. And you have the crate. Okay. Now here, okay, so initially the truck was at rest. Okay. And then suddenly it moved forward. Sorry, it moved forward. So that means velocity is to the right, and also for it to start from 0 velocity to a certain velocity, we must have applied an acceleration. Okay, to increase the velocity. Now here the crate will have the tendency, of course, according to inertia, okay, to move backward, of course. So the crate will want to move backward because it wants to remain, okay, stationary at rest, okay, according to its initial state. Now here, which of the following then statements is true regarding the motion of the crate? And we're choosing option A, which states the crate slips back because the frictional force from the cargo bed is not large enough to keep the crate moving with the same forward acceleration. So we do have a forward acceleration here, okay, as the truck. Now, of course, for the truck not to move backward, I need what? I need a friction force that is pointing forward. Okay, so I need a friction force, but because there's no friction, the crate now is moving backward. Okay. Right, question number 4. A truck moves forward with a constant speed and has a crate in its cargo bed. If the truck suddenly slows down, okay, and the crate does not move against the cargo bed, in what direction is the frictional force that the floor of the cargo bed exerts on the crate? Okay, now similar. I think we had a similar question in 2018. Now let's try to picture this again. This is the truck, roughly. With a pen here. The truck, the crate, okay. Now the truck is moving forward with a constant speed. Initially we have the constant speed v, and then of course with the crate in its cargo bed. Now the truck suddenly slows down and the crate does not move against the cargo bed. Okay. Now slows down means what? Slows down means slows down means I have acceleration that is pointing in the opposite direction. So the truck is slowing down. That means I have an acceleration that is pointing backwards. Okay. If that's the case, the crate will want to move. The crate will want to move forward. Okay. So if acceleration is backward, the truck wants to slow down, but the crate wants to carry on with the same velocity. So it wants to move forward. Now here we're saying, okay, but the crate does not move against the cargo bed. Now what does that mean? If it wants to move forward and it doesn't, now I must have a friction, or it must be because there is a friction opposing that motion, that forward motion, and it has to be pointing backward in the opposite direction. So I'm putting it in blue here. Friction, okay, pointing backward. So that's why the correct answer is this one here. Okay. Now, next question. Question 5. Which of the following statements include all of the essential elements of Newton's first law? Of course, Newton's first law says a body persists in its state of rest or uniform motion in a straight line unless acted upon by a non-zero net external force. Okay, so this one includes all the elements of Newton's first law. Now, the others, okay, so the others may include some aspects, but not all of them, okay? Like first one, a body persists in a state of uniform motion in a state as long as the net external force remains constant. Now, what's wrong with this one? So here, it doesn't include the state of rest, just uniform motion, okay? Now, the second one, a body persists in a state of rest as long as the net external force remains constant. So this one, the second one, only talks about the state of rest and does not include the uniform motion. Option C, a body at rest persists in a state of rest unless acted upon by a non-zero net external force. Same thing, not all the elements are there. So only option D is including all aspects, okay, or all the elements of Newton's first law. Now, question number 6. An object is moving with constant velocity. Which of the following is true? Okay, so it's moving with constant velocity. Now, if it's moving with constant velocity, that means it's in equilibrium. And equilibrium means the net force on the object is 0. So that's option B. All right, so something also we talked about countless times. Now, let's move on to the next one. We have the following: a block of mass M1, 12 kilograms, okay, and another block of unknown mass, M2, and we're assuming that M2 is less than M1, are connected by a light string or a massless frictionless pulley. Now, if the system has an acceleration of 6 meters per second squared, find the tension in the string. Find the tension in the string. Now, here, what we need to do is we need to apply Newton's second law on either sides, or the sides that will give us, okay, a direct indication about the tension. Now, in this case, if I move down, so if we apply Newton's second law to mass number 1, okay, so for mass number 1, so we're having the following. So tension minus M1. Okay, so again, we're given the mass M1 as 12 kilogram. Let me just delete the notes. So we're given the mass M1 as 12 kilograms, so the mass here is given. Okay, now knowing that M2 is less than M1, so that means M1 will be driving the motion. So that's the mass going to be driving the motion. Now, of course, I have the same tension on both sides. Okay, so I have the same tension on both sides, which means if I apply Newton's second law on mass 1, so this will give me, again, if I choose positive y pointing up, here, net force along y is equal to mass times acceleration. Now, acceleration, I'll take it as negative, pointing downward. Okay. So the forces will be tension, positive, because it's pointing up, minus M1 mg, because it's pointing down, equals to M1 times the acceleration, which is, in this case, going to be taken as -6. Okay, it's pointing down, so I take it as negative. Now, in this case, all I have to do is take mg to the other side of the equation and then factor mass 1. So I end up with tension equal to M1 times 9. Sorry, G, not 9. So this is gravity, G. So gravitational acceleration, G, minus 6. Okay, now the rest is easy. Just plug the numbers corresponding to the mass, and you get your tension. So here we go. So just plug the mass 12 kilograms and G 9.8, and you get your tension equal to 46 newtons. Now, question number 8, also straightforward. All we're doing here is we're applying a horizontal force of 170 newtons to a 64 kilogram crate on a rough level surface. Now, if the crate accelerates at 1.2 meter per second squared, what is the magnitude of the force of kinetic friction acting on the crate? Now, here, it's exactly similar to what we had in midterm 2018 we covered today. With the only difference is we don't have an angle for the force. Okay, so here we don't have an angle for the force. So let's say, bring the pen. So the force here is just horizontally, which makes things even easier. So the net force along x is equal to mass times acceleration. So I'll have the acting force as positive minus friction. Now I take it as Fk, of course it's kinetic friction because it's moving, equals to mass times acceleration. Now that means, again, the friction, what is the magnitude of the force of kinetic friction acting on the crate? That's what the question wants. So all you have to do is take friction, negative friction to the other side, MA, okay, to the left, swap the both sides, and you end up with this friction equal to force minus MA. So plug in the numbers and you end up with this 93 newtons. Okay, again, straightforward. Right, so question now number 9. Question number 9, we have the following. If the tension T, okay, is 15 Newton and the magnitude of the acceleration A is 3 meters per second squared, what is the mass M? Okay, so this lowercase m of the suspended object. Assume that all surfaces and the pulley are frictionless. Okay, now here we are provided with a tension, okay, in the string, okay. So I'm provided with a tension equal to 15 newtons. We don't know the mass. And we're also provided with the acceleration. Now, if I apply Newton's second law on the suspended mass, so that will be net force along y will be equal to mass times acceleration along y. Now, I'll take positive y here, positive y pointing up, okay, which means tension will be positive, mg will be negative, okay, so we're used to this by now, is equal to mass times acceleration. Now, because it's accelerating downward, I'll take the acceleration as -3, okay? Now, tension in this case, you can, of course, the unknown is the mass, so you need to take mg first to the other side, factor the mass here, okay? And then, of course, this is what I'm looking for, the mass, which means we take this term, g minus 3, you take it downstairs under the tension, so you end up with mass equals to tension divided by g minus 3, okay? So that means the mass is equal to 15, which is the 15 newtons for the tension divided by 9.8 minus 3, which gives me 2.2 kilograms for the mass, okay? Right, so this is then for question 9. Now moving on to question number 10. The question related to center of mass. Now we're asking you to calculate the x center of mass of this 3-particle system. Now these particles, are arranged on a two-dimensional plane. Now, where mass number 1 is at the origin, so the coordinates are 0, 0. Mass number 2 is 5 kilograms, and it's at 2.55. Mass number 3 is 15 kilograms, and it's at 5, coordinates 5, 0, 5 along x and 0 along y. Now, we use the formula for x center of mass. Again, straightforward. We did this many times. So m1 x1 plus m2 x2 plus m3 x3. And it's a matter just of plugging the values for mass 1 x1, mass 2 x2, mass 3 x3. And in the denominator, we're adding all the masses. So plug all these numbers into your calculator, you get this value of 2.9. Again, straightforward. Question 11. We did this many times. A valid unit for momentum is which of the following? Now, momentum is given by the formula P equal to mv. Okay. Now, among these, right, option, of course, this is what? This is kilogram for the mass. And then for velocity, it's meters per second. Now, of course, the option is option D. All right, so this is the option corresponding to the momentum in this case. Now, question 12, when a collision is perfectly inelastic, then among these options, we have option E, which says the participants stick together. Okay, so this is when you have a perfectly inelastic. Okay, so this is before collision. Let's say we did this also many times. This is mass 1, this is mass 2. Let's say mass 1 is moving with V1 initial. Mass 2 is not moving, V2 initial. After collision, this is before, after collision, they move together. They lock to each other like this. And they move as one. Okay, as one block with a total mass m1 plus m2. Okay, so this is how we define perfectly inelastic. Now in this case, okay, so this is the correct option. Now why the others are not? So option A says all the kinetic energy is conserved, which is not true. Okay, when you have perfectly inelastic, the two objects stick together, which means some of the energy is lost in the process of sticking. Okay, could be turned into heat, could be turned into internal losses or stresses, etc. So all, part of this kinetic energy will be lost in the process. Now, second one, all the kinetic energy is lost, which is not true. If it was all lost, okay, and what would happen is probably the two objects will lock and they will stop. The total momentum is 0. That's not true, okay, because the total momentum will have a component, okay, due to the first mass moving, right? So the total cannot be 0. Even in perfectly inelastic, we know total momentum is conserved. And the momentum here says it's not conserved. One second. So the momentum here says it's not conserved, okay, which is not true. The momentum is conserved in this case. Right, so that's then question 12. Now question 13. Now we have this from midterm 2019, if I'm not mistaken. So this is a squid ejected bolus of water in order to escape a predator. Now the squid has a mass of 1.4 kilogram. Okay, we're calling it mass squid. So we're calling it MS, or which stands for mass squid, with its water cavity empty, and then needs to escape with a speed of at least 0.7 meters per second. Now, if the ejected water has a mass of 0.5 kilogram, okay, so let's call this M water, how fast must it be ejected in order for the squid to escape? Now, I have a mass, or this is velocity squid, actually. So it's not mass squared. So this is velocity squared. Okay. So we want then, how fast must this be ejected for the squid to escape? Now, of course, before the water is ejected, okay, nothing is moving, the total linear momentum is 0. And after, okay, after the water is ejected, of course, it's ejected to the left, backward, so that the squid is moved forward. Now, here, we're looking for velocity water. This is the unknown, velocity water. This is what I'm looking for. At what speed must this water be ejected so that the squid goes forward at this speed of 0.7 meters per second. Now, this is then the question. Now, in this case, before the water is ejected, the total momentum is 0. After it is ejected, okay, so the total linear momentum would be mass water, velocity water, plus mass squid, velocity squid, okay? Now, in this case, the total linear momentum before or initial, so it should be equal to the total linear momentum after. Now, before, nothing is moving, so it's zero for both the water and the squid. After it is ejected, so I'll have mass water times velocity water, okay, plus mass squid, velocity squid. All right. Now I know the mass of water. Now velocity water I don't know. And I know the mass of the squid, 1.4 kilograms. And I also know the velocity of squid at which he needs to escape. So I solve then for velocity water, okay, which will give me velocity water equal to negative 1.4 times 0.7 divided by 0.5. And this will give me a negative velocity of negative 1.96 meters per second, okay? Or you can round it to about 2.0 meter per second, okay? Now, these are two significant figures, all the options here, or the option C here, the closest answer is the 2 meters per second. Right, so this is question 13. Now, question 14. Now, it's similar to the one we had today from midterm 2018. So we have maybe a slight difference for the masses. In fact, this is even easier because the two masses for the two cars is the same. So we have a 12 kilogram, or 1200 kilogram car. This is M1, approaches an intersection traveling east at 30 meters per second. Now these are the vector components for velocity 30 and 0 meters per second. And then another 1200, okay, kilogram car approaches the same intersection traveling north at 32 meters per second. Okay, so these are the vector components, 0, 32. Now the two cars collide at the intersection and lock together. See the figure below. Ignoring any external forces that act on the cars during the collision, what is the direction angle theta? And we're looking for theta, so that's the difference between what we had in midterm 2019. We're looking for the direction angle theta of the velocity v final of the locked cars immediately after collision. Now here, we're looking for the theta. Now, we proceed in a similar way we did for the question we had in 2019, in the sense that total linear momentum is conserved, okay, before and after the collision. So this is initial equals the total linear momentum after collision. Before collision, you have M1, V1 initial plus M2, V2 initial is equal to total mass, M1 plus M2 times V final. Okay, now, of course, in this case, you write this in vector notation. So you have M1, the 1200 times 30 for velocity 1, x component of velocity. So x component of velocity 30, and then 0 for the y component, and then plus M2, which is also 1200 times vector components, 0 for the x component, 32. And on the other side, you have M1 plus M2. So that's 2 times 1200. It's the same, okay? Which means what we can do is we can just cancel the 1200 everywhere. All right, so the 1200, we can just forget about it. We can add the vector components. Now you end up with 30 for the x component and 32 for the y component, equals to 2 times v final. Okay, now that means v final will be just the vector components you have on the left side. You just divide them by 2. Okay, so you take this 2 here downstairs under the 2 vector components on the left side. So you end up with vector components for final velocity as 15 for the x component and 16 for the y component. Now here, if you have the 2 components, right? Remember we discussed this in the lecture. We said if you want the angle theta, you know that tan theta, now of course the theta here will be the angle corresponding to v final. So let's say if this is v final for the 2 cars moving together, and it's making an angle theta with the horizontal. So the v final along x, let's use a different color. So I have v final x, and I have here, if you project along y, you'll have v final y. V final y. Now, of course, the y component of velocity is the opposite side in this right angle triangle, and the vx is the adjacent. Now, you know that tan theta will be then, okay, will be then equal to what? The opposite over the adjacent. Okay, so that will be v final y, that's the opposite side, over v final x. Now that means if I want theta, all you need to do is apply the inverse tan to the y component over the x component, and this will give us 46.8 degrees, okay, which corresponds to option A. All right. Okay, so I hope it's all clear. Let's carry on. Now, question number 15. We have a bar of length L equal 3.4 meters is pivoted at one end, point P, and the force F equal 11 newtons is applied at the other end, as shown in the figure. If the angle alpha is 30 degrees, find the torque of this force about the pivot point P. Now take counterclockwise torque out of paper as positive and clockwise torque into the paper as negative. Now, in this case, okay, so in this case, like we saw today for midterm 2018, okay, so for 2018, what happens, where's my pen? 1 second, choose red. So what happens here is you see the direction of the force, okay, the direction is given relative to the vertical. So alpha here is given, was provided relative to the vertical, and we did this in we talked about this in midterm 2018. We said it's still the perpendicular component of this force that is causing the torque. This is the perpendicular component. Okay. Now here, okay, so here if this is the perpendicular component, and the angle alpha is given with the perpendicular, also with the vertical, that means what? If you take this triangle, now the F perpendicular in this case is not the opposite anymore to this angle alpha. The F perpendicular is now becoming the adjacent, which means this component will be F, not sine, but cosine theta. Okay? If you remember, the torque is defined as R times F perpendicular. Okay? Yes, it is RF sine theta. That's provided the theta is relative to the horizontal. But because now theta, or the angle alpha, is with the vertical, the perpendicular component of force is now with the cosine. Okay, so here, that means when you calculate the torque, you need to be careful if the angle is provided with the vertical. It's not going to be the sine anymore. Okay, so it's going to be the cosine. Okay, so it's going to be the cosine in this case. So torque of this force, okay, relative to the pivot point P. So torque relative to pivot point P is equal to F cosine alpha multiplied by the length. Okay, so in this case, the distance from pivot point to the force will be the length L, which is the 3.4. Now the rest is easy, just plug in the numbers. 11 newtons for the force, cosine 30 degrees, and times the length, which is 3.4. Okay, so ending up with 3.2 Newton meter. Now, the sign, is it positive or is it negative? The question is, or we're specifying that if it is counterclockwise, it is positive. If it's clockwise, it's negative. Now, the force is causing here a rotation that is counterclockwise. So if it's counterclockwise, of course, the torque will be positive in this case. So counterclockwise, we're dealing with a positive torque. And this is then option E. All right, so that's then question 15. Now let's move on to the next question. Which expression describes translational equilibrium? Now, translational equilibrium is when an object is moving linearly. So we're dealing just with a translation or linear motion. So in this case, the object is not allowed to rotate. Okay, so when is this object in equilibrium? Moving with either constant velocity or velocity equal to 0. Okay, only when the net force equals to 0. That's translational. So there's no rotation or rotational component in this motion. Okay. Now, question 17. We have two children see themselves on a seesaw. Okay. Now, the one on the left has a weight of 400 newtons, while the one on the right weighs 300 newtons. The fulcrum is at the midpoint of the seesaw. Now, if the child on the left is not at the end, but is 1.5 meters from the fulcrum, and the seesaw is balanced, what is the torque provided by the weight of the child on the right? Now, take counterclockwise torque as positive and clockwise torque as negative, as usual. Now here, again, we're looking at, use the pen. So here, we're asking you, what is the torque provided by the weight of the child on the right? Okay, so here, we're taking, of course, the net torque equal to 0, and it's balanced, and it's around the fulcrum here, okay, equal to 0. Sorry, this is the point C. So it's equal to 0 here. Okay. Now torque then, due to the child that sitting on the left, the 400 Newton, and then the torque due to the normal, of course, here is 0. That's the normal on the fulcrum. Okay, so that does not apply any torque. Okay, so that goes to 0. And plus the torque due to the 300 Newton child on the right. Now in this case, we're not provided, okay, with the distance at which the child on the left is sitting, but I want to calculate the torque that this child is applying. So provided with the 1.5 meters for the child on the left. Okay, so that means what? First, let's not forget the directions. Now, child on the left is applying a rotation that is counterclockwise, like this. Okay, so here, so it's going to be a positive. So this is counterclockwise. So CCW, okay. And for the child on the right, so for the child on the right, it's going to cause a rotation that is clockwise. So here, for the counterclockwise, I'm taking it as positive. And for the clockwise, that's for the child on the right, I'm expecting this to be a negative torque. Okay, so when I do that, again, I'm looking for this torque. This is unknown. I just put a plus here, but I'm expecting it to be a negative value. Again, it's still a plus here, torque due to the 300. I'm putting a plus, but when I end up with a value, I'm sure I will end up with a negative sign. So here you will see 400 times 1.5. You take it to the other side of the equation. Okay, so you end up with 400 times 1.5 is 600. 600 taken to the other side of the equation will turn into negative 600 Newton meter, corresponding to option B. So that's question 17. Now, question 18. We have the following: a person holds a 140 Newton dumbbell in his right hand. His forearm and hand are held stationary in the horizontal position with no rotation at the elbow joint by the force F from the bicep muscle, making an angle of theta equal to 11 degrees. Okay, we are here. So theta 11 degrees. Now the angle is provided with the vertical. So pay attention to this. The angle is with the vertical. Now it's not very, very clear. The force is like this. So I will highlight it to make it clearer. So the force is like this from the bicep muscle, and it's making an angle theta. So I'll use maybe green to show the angle. So this is the angle theta, and this angle is with the vertical. So theta here is with the vertical. Okay, right. So if that's the case, again, the fulcrum is at the level of the elbow, and we're given the distances. So here, from elbow to the force applied by the bicep, I have 4 centimeters. And here I have the distance from elbow to where the dumbbell is 35 centimeters. Okay. Now to make the system look simpler to study, we convert all this arm and dumbbell, etc. We turn it into a simple lever system, just with a bar like this. Okay, so just a simple bar. The fulcrum is on the left, and here, this is the fulcrum, point C, okay? The force is at an angle theta with a vertical. So the angle theta with a vertical. And you have the weight for the dumbbell. Now, there's no other weight acting. We're saying ignore the weight of the forearm itself and any other muscle forces. And we're asking you to find the bicep muscle force. Okay, so find the bicep muscle force. So my unknown is this force from the biceps to balance the system. Okay, so the starting point will be net torque equal to 0 around the elbow. Okay, so axis of rotation is around the elbow. Now here, the torques involved will be torque due to force plus torque due to weight. Okay. Plus torque, probably we're talking here any other forces acting on the elbows. But these ones, okay, these ones will be 0. Okay, so these ones will be equal to 0 because they'll be acting directly on the fulcrum, and those will be again 0. Whatever force is acting on the fulcrum will have a 0 torque. Now, which torques are positive, which torques are positive, which torques are negative? Now, the torque due to weight, we'll start with this, is causing a clockwise rotation. I'm sure you will all agree this is clockwise rotation. Now, for the force, so here for the force, you see it's causing a counterclockwise rotation. Now, bear in mind, what is causing the rotation is this vertical component of force, F perpendicular. Now, and if you notice the angle, like we said in the previous question, the angle theta is with the vertical. So F perpendicular will be equal to F cosine, in this case, cosine theta. The angle is not provided with the horizontal. That means what? Okay. It's a positive torque, and I have to express it with the cosine. Now, let's put this down. So in the net torque, I have force, is red. So I'll have force. I am here. So force, okay, we'll get there. So force times cosine theta times the distance from fulcrum, okay, to where the force is acting, and then minus the torque due to the weight of the dumbbell. So that will be your mg. This is the weight. It's directly given in newtons, 140 newtons, multiplied by 35. And the angle, because the angle is 90 degrees. Okay, so the angle is 90 degrees between the force and the arm of this lever system. So 90 degrees, sine 90 degrees is 1. Well, we have 1, that's why we don't see the sign. So equal to 0. Now, the unknown in this equation, the unknown is the force. So all we need to do is solve for the force, which will give me the following. Which will give me a force equal to 1250 newtons. That's after plugging all the numbers in. Okay. Again, it should be straightforward. Once you put the net torque clearly with the properly, taking the direction of the forces and paying attention whether the angles are with the horizontal or the vertical, which means you know exactly whether you're using sine or cosine. Okay, so be careful when you have a question like this. Okay. Question 19. A person doing a push-up, okay, on a horizontal floor is an example of a class 2 lever system, something we have seen in midterm 2019. Remember the picture of the person doing push-up from that midterm, and we had a class 2, and we said class 2, okay, corresponds to, let's say this is fulcrum here at the level of the toes, okay, the feet or the toes, and then the body weight, okay, comes right next to or just after the fulcrum. Okay, so the weight or the load is closer to the fulcrum, and then on the opposite end of the fulcrum you have the effort, and that's the effort done at the level of the elbow, okay, with the arms, okay, so using all the muscles of the arm, biceps, etc. So that's the effort. So this type of lever system is a class 2. Okay, class 3 is when the effort is closer to the fulcrum, right? Okay, now last question. Last question in this midterm is the following, question 20. Now we have the following: even when the head is held erect, as in figure, now its center of mass is not directly over the principal point of support, the atlanto-occipital joint. Now the muscles at the back of the neck should therefore exert a force to keep the head erect. Now that is why your head falls forward when you fall asleep in the class, for example. Okay, calculate the force Fm, force muscle here, okay, exerted by these muscles, trapezius, using the information in the figure. Now, we're provided with all the numbers, okay, so the fulcrum is here, point B, right? Then you have force muscles is at 5 centimeters from the fulcrum, acting at point A. And then the weight of the head here is at a distance of 2.5 centimeters. Okay, and the weight is 15 newtons. Weight is 15 newtons. Now, we're asking you then to find the this force due to muscles, okay, which will balance the head in this case. Now, same idea, net torque equals to 0 around the fulcrum at point B. And in this case, the torques will be first torque due to Fm. Now, this torque will be counterclockwise, will cause a rotation that is counterclockwise. So that means positive. Now, the torque due to the weight will be negative because it will cause a clockwise rotation. That's a CW, okay? Now, this is going to be a negative torque, so torque here will be negative. Torque due to weight, to be more specific. And this is torque due to force muscles is positive, all right? Now, the net will be torque due to force muscle, plus again, torque due to a reaction on the fulcrum. And of course, here, this will be 0 because it's acting directly on the fulcrum. And plus the torque due to the weight equal to 0. Now, I know that torque due to weight is negative. I'll put a negative sign for the weight, or the torque due to weight. So it's the 50 newtons multiplied by the distance, and the angle is 90 degrees. Now, as usual, sine 90 degrees is 1, so that's why you don't see the sign here. And on the other end, you have a positive torque. Okay, positive torque due to force muscles, so that's force muscles, times the 5 centimeters, okay? And the whole thing is equal to 0. Now, the unknown is force muscles, so you solve this equation for force muscles. Now, you solve it for force muscles, and you end up with you end up with force muscles equal to 25 newtons. So this is then the last question in this midterm, and we practice in this midterm many of the concepts, okay, we discussed in all the chapters 4, 5, and 6. Now, there's still some questions related to chapter 7. Now, these questions will be in midterm 3, or past year's midterms 3. Now, I will probably record some questions related to those, okay, and so expect these videos probably tomorrow. Thank you very much then.